Okay, this system of masses on this beam balances at this point. This point being (32.5 centimeters) from that end. Now, I didn't measure that real carefully, but it could be measured much more carefully. The mass of the beam and the magnets is, lost weight, 390 grams. I said 408 before, so go ahead and use that. But I'm going to use 390 if I remember it when I do this on the board. Okay, now I want the center of mass to move to here. In order to make that happen, I try to balance it with a single domino at this end. Well, it doesn't even come close. Two dominoes, a little better, but not quite. Three dominoes overbalances it. To move the dominoes in this direction, and whoops, that's what it was, a little too far. Maybe here. Okay, now the system balances. It balances at a point 34 centimeters from that end. And the three dominoes are, well, let's see from this end. Yeah, 52.5 centimeters from that end. So what's the mass of those three dominoes? I can easily figure that out. What did I say was 390 grams? I could lift this thing off. Well, actually, I can read it on the scale, but you can't from where you are. So it's still a mystery to you. And we'll see how close it comes out. Okay, now we're going to focus the camera back on the blackboard and see what this looks like. So here's a picture. Domino about here. Magnet about here. Magnet about here. Okay. Mass of the original system is 390 grams now. So if you worked out for 408, that's okay. I don't know what the difference was. Looks like the difference is a plate of a domino, but it shouldn't have happened. Anyhow, center mass is at 32.5 centimeters. Call this end A. Center mass relative to A. 32.5 centimeters. And that's maybe here. So when the fulcrum is here, the total torque about this point is zero. Wherever the fulcrum is, if it's balanced, the system is balanced, then any system in equilibrium has net force acting on it is zero. You can, gravitational force acts down the scale or whatever the thing's sitting on acts up. No forces in the y direction, no forces in the z direction. And the torques. You got those four conditions of equilibrium for any situation, any object, or any system of objects. So we might want to write that down. Sum of the forces in the x, y, and z directions is zero. Those are the equilibrium conditions, and sum of the torque is zero. Just like the equations of motion with a projectile, the first thing you want to do when you have an equilibrium situation with masses and so forth is write down the equilibrium conditions and work within that framework. Okay, well, so anyhow, originally zero torque about the center of mass. Now we have mass M so that we balance about a point at 36 centimeters. Dash to let myself more room, but so the new center of mass is here. So now the system will balance a new fulcrum and a new center of mass. What torques do we have? We have the torque of this force, which is the weight of the original system. And we have the moment arm perpendicular to the line of that force. The center mass perpendicular to the line of force. Okay, this moment arm, don't have a good place to label it. But it is what it is. So there's your moment arm, there's your force. There's your picture. Here's your new mass. I didn't write the position of the new mass, but it's 52.5 centimeters. So here's the weight of the new mass. And here's its moment arm. So what we now have about this 34 centimeter position is we'll call this R1, we'll call this R2 equals what? It's the 52.5 centimeters minus 34 centimeters. That's 18.5 centimeters. I'm going to actually put an arrow over this and call it negative 18.5 centimeters. It's 18.5 centimeters in the negative X direction, if you wish. And then I have I'll call it MG. Okay. Over here, I have this moment arm. Well, 34 to 32.5 centimeters. .5 centimeters. 390 grams times G. Well, by the right-hand rule, R1 across this mass is into the board. R2 across this mass is out of the board. This is a positive Z direction, if you wish. It's a negative Z direction. So we can say that the net torque that's a vector actually. It's yes. Okay. Sorry. That's a net torque. I'm getting ahead of myself. I don't really need that. That would be the equation from center of mass relative to the center of mass, which would be 0. And that's equal to 0. I'll put an arrow over this tile net because I'm using signs. And this torque is along the z-axis. Both torques are along the z-axis. This in the positive, this in the negative direction. But I'm not really worried about the z-axis, the I-can cable in this particular example. Okay, so there's your net torque. Then I have mg here. And the way I want to divide this. All this times the acceleration of gravity. But of course, this G is confusing with this G. And there's notation. Your book has a notation to distinguish grams from P or gravitational acceleration G. Just understand from context that both of these, you have an mg here, and you have 390 grams times G here. Those are your forces. Some of this is 0. So you never needed to write that in the first place. And how we solve this for M? Pretty simple. M is 390. I don't need to write it up there, but I did. So. A simple algebra. Okay, 1.5 over 18.5 is about 1/12. 12 times 1.5, 12 times 15 is 180. Okay, that's about 1/12 of this. 12 goes into 360 20 times. What does not think about anywhere near? It'll be about 22, 21 or 22 grams. And well, actually, I think about 45 grams in reality. I didn't think I'd measured things that poorly. But if I revise my measurements, it's gonna go over here. Try to make a closer measurement. Take the meters, get all that. Close. Probably more like 1.3 centimeters, 1.5. But it is what it is. With accurate measurements, this would reconcile very nicely. Okay. Now, you see how in the first place, starting with some of my torques about the fulcrum equal to 0, gave me the result. You can verify for yourself that I could have done all the torques about this end. But then I would have had to include the force exerted by the fulcrum. So let me draw the alternative picture. Right here at the end of the. In that case, we would have the weight, total weight of the system acting at the original center of mass. We would have the force exerted by the fulcrum acting at the new center of mass. And out here we would have mg. The symbols, this total weight acts at the original center of mass. The force of the fulcrum acts at the new center of mass. The mg acts at where is it just like position X. The moment arms are measured from A. So for example, the moment arm of the total mass, total weight is here. The moment arm of the force and fulcrum is here. And the moment arm for mg let my arrow go to my arrows. Okay. Here. I have to arrange the picture a little more in advance. Didn't know this was what I was going to do, but when I found out there's not going to be doing the Zoom. Okay. And that's fine. This is working out just fine. Okay, so we have these three. And now we have, first of all these torques are positive. Okay, for the right hand rule. So we have explicitly, I'm going to call this R sub W, that goes with the split W. Then we have the total weight plus mg, which is equal to the force exerted by the fulcrum because of this condition that I haven't written out, but it's kind of implicit. We seem to kind of understand that. But formally, you'd want to write this condition now so that you know what this force is. Sum of all the forces has to be 0. So that this has to equal the sum of the weight of the system and the weight of the added mass. And then we have I'll use RM for moment arm of the mass. Now, RW we know to be from A to here, 34 centimeters, right? And our fulcrum we know to be, I'm sorry, RW is the original fulcrum, position the original center mass, which is 32.5 centimeters. 34 centimeters for our fulcrum and 52.5 centimeters, what I write it somewhere here, 52.5 centimeters for the R of the added mass. Okay, you should work that out. I mean, it takes maybe 2 minutes to solve. Okay, and let me point out, this could be solved for, well, how many things here don't we know? We don't know the added mass. Okay. Oh, that's the only thing we don't know in this case. Now, it could be that we ask the question, where do we need to position a given mass to balance the system? In which case, R sub M would be unknown, but we would know the mass, right? So either of these could be your unknown with the rest of the measurements. So if I want to move the center mass to 36 centimeters, now knowing the mass that balanced it at 34 centimeters, I would know the mass, and my new RM would be the only unknown in the equation. Okay, so you want to try to understand that. Again, everything comes back to these conditions. Sum of your forces in each direction is 0. Sum of your torques is 0. Okay, where am I? Where's the record button here? Oh, that wasn't recording. Okay, we have another system here. We have this bracket. There's a magnet up here and there's a strap, which a lot of people recognize is a strap I cut off of my mask because it was flopping around and injuring people, especially me. That really wasn't doing any harm, but it was irritating. So now I've got these nice elastic, basically a cross between a rubber band and the springs, with properties somewhere between those, the rubber band and the springs. Okay, well, I'm gonna, right now, thing is pretty much flat. At this point, it's obviously exerting some torque because this paper clip was kind of attached to the metal, residual magnetic field and stuff. Okay, I've got two paper clips. I can associate the force exerted here by the distance with the distance between the paper clips. All I have to do is hang different weights in the end of this thing and observe how far apart the two paper clips are. They start exerting force when they're, a little hard to measure this, about 20 centimeters apart. So right now these things are separated by 20 centimeters. Now I pull this back a little bit. And well, we're still in equilibrium, aren't we? Still in equilibrium, so the sum of all our forces in the x direction, and the sum of all our forces in the y direction, and the sum of all our forces in the z direction. We're not going to worry too much about z, because we're going to put an xy plane here and let z be in this direction. But all the forces in the two relevant directions, the x and the y direction, the two linearly independent directions of space, according to the coordinate system we'll want to set up. All those forces are adding up to zero every time. Now we pull back a little more. Now we can tell that there's definitely a force here. We haven't calibrated this thing, but those paper clips are now about 23 centimeters apart. There's definitely some force being exerted. So now we pull back a little. Oh, look at that. And now we no longer have rotational equilibrium. It looks like it almost wants to slide along the tabletop. Now we can measure the coefficient of friction between the tabletop and the metal. Let's say it's probably in the 0.25 range. But that's just a guess. I can measure here and see that this is now separation of these two paper clips is now about almost 24. Okay, well, I can pull back a little further. And once before, it is tending to slide a little bit, but not too much. Okay, and now the separation here is down to about 23.5 centimeters. Okay, so it's less than it was. Why is that? A little further. And yeah, down to about 23 centimeters. Fudging that a little bit, this is for illustration. Okay, here. A little under 23 centimeters. This hole pretty close to 23 centimeters. Isn't changing much. Now notice, why is this length pretty much not changing over the last few measurements? Okay, it's been right around 23 centimeters, actually below 23s. Well, think about the fact that this angle here keeps changing. The angle between the elastic band, call it, and the horizontal. Of course, I mean, well, here's training as well. So how does all that go together to explain what we're seeing and explain maybe that the tension doesn't seem to be reduced yet? Now, something's going to happen here shortly. We're going to have a disaster. Can you anticipate what that disaster might be? Still around 23 centimeters. They can't detect a whole lot of difference in the last 4 or 5 measurements. Something's got to change. Aha. There's definitely a bit of a change. Probably down maybe at the 22.5 or 22.6, 22.7 centimeters. A little hard to measure this because everything's in the way. I could have set it up differently to make it easier to measure and would if we're doing this experiment. Okay. So we go a little further. Ooh, look at that. Okay. It looks like it's definitely down below 22.5. Okay. Are you feeling uneasy about anything here? Is anything likely to happen? Oh. Doggone it, I wish I'd have gotten that measurement, but I clumsily tweaked the elastic band, and that's all it took to break well, what happened? We broke static friction. Now we have kinetic friction. This thing accelerated down the middle surface, delivered an impulse here, an angular impulse that could be calculated from data that we could take from what we just saw. If you know the thickness of this thing, and just get our fence if anybody's interested. The thickness appears to be 0.8 centimeters. I could get a better measurement of that, but staffing several of them. There's 3 of them. 3 of them stand on 10 centimeters. 12.6 centimeters, which is almost 0.9 centimeters apiece. But anyhow, angular impulse, an angular change in the angular momentum of system, so that the angular velocity of this tipping bracket had a more or less discontinuous change. It subtly changed from one value to another. Now that was actually continuous. It was a very short time frame, so you pretty much treat it as a discontinuous change. All kinds of interesting things happen there. And I wonder how many of them you can see. Okay. Well, there we have what's really a pretty interesting situation, but how do we analyze it? So what I'm throwing out is what can you see in the system? What diagrams can you make for different phases of the system at different positions, different angles, and so forth? We don't have good measurements to analyze it, but pictures that you can get, the pictures of forces, torques, etc. Well, those things can form the basis for very interesting investigation. So, address the camera. Okay. So what do we see in this situation? So I'm asking everybody to sketch a set of good pictures. Incidentally, see an elastic band here that was trimmed here and down here. It was hanging all over the place. And that's where that thing came from. We haven't yet calibrated it, but it's very easy to calibrate. Just hang different weights, see how far apart those paper clips go. Okay. That's it. I'm not going to do anything at the board today. We might well pick this up at the board next time, especially if people come in with some interesting pictures, some pictures that might need some modification. I want to see what people can do with this whole situation. The key in the present chapter, which is a lot of statics and Young's modulus and stuff like that, and rotational equilibrium. Really requires some good pictures. Really requires you to be able to sketch free body diagrams. So work on that a little bit. Okay, very good. Look forward to seeing everybody next time.